So this is the second video on molecular geometry for you guys, and this is the video the slide we left off with, which was counting electron domains. So you remember we are concerned only with the central atom right here. So we have our carbon, we have one bond and one bond. We get a domain of 2. We jump to the xenon, you get a bond of 1, a bond of 2, and 3 lone pairs, 3, 4, 5, for an electron domain of 5. So the next thing we're going to do is we're going to use that to predict molecular geometry. Alright, so this is what they look like three-dimensionally. Electron domains, 2, you get linear. 3, you get trigonal planar. That prefix tri means 3. And planar means they're all in the same plane. So I could take a knife and I could slice these and get them all to be symmetrical. Tetrahedral is 4. These are not planar because even though I could slice this way and cut these 3, this one is going to be different. I won't be able to slice that one equally with the other 3. So planar means they're in the same plane of existence. Alright? We can keep going and we get trigonal bipyramidal and octahedral. These ones I will be less concerned about you knowing because these have some very odd shapes that for you guys it's not worth spending too much time on some of these more complicated ones. So now we're going to do the molecular geometry, which is slightly different. So let me get out of this for a second and go to my chart. So electron geometry, electron geometry is number of domains. Right? We just care about the domains. Molecular geometry, though, says we're going to be a little more specific. We are going to split it into bonds and lone pairs. So how many bonds do we have? How many lone pairs do we have? That's what molecular geometry says. That's an L and an E, by the way. That's not a K. That's not molecular. That's molecular. All right. So number of bonds and number of lone pairs. So we are going to use ammonia as our example. And this kind of came out a little odd. So let me clear the board and show you what it should be. So ammonia has 1 lone pair and 3 hydrogens. You may remember ammonium as one of your polyatomic ions from the last test. That is NH4. That has 1 more hydrogen than ammonia. So this is ammonia. Alright. And its molecular geometry is based on its electron geometry. So its electron geometry, it has 1, 2, 3, 4 domains. So 4 domains. So it's tetrahedral, right? Tetrahedral. But what is its molecular geometry? Well, let's take a look. I'm actually going to jump ahead a little bit because I think the next slide does it much better. So, ammonia would actually be trigonal pyramidal. Okay? So, to back up and explain how we got there, these are your electron geometries. These 5, right? These are your molecular geometries. So if you have a linear electron geometry, you have to have a linear molecular geometry. Because remember, these electrons are as far away from each other as they possibly can be. There's no reason to move this around, because then they would actually be breaking the VSEPR theory. But if we go to a third domain, either a bond or a lone pair, we get bent or trigonal planar. So look, the name for 3 electron domains is trigonal planar, and we can even have a trigonal planar as your molecular geometry. And you see tetrahedral, octahedral, and trigonal bipyramidal. So in fact, your molecular geometries may match your electron geometries. They may be called the same thing. That happens quite a bit. So, if we have planar as our electron geometry, we'll either have bent or trigonal planar. If we add another domain, so we're up to 4, we'll have bent, trigonal pyramidal, tetrahedral, so on and so forth. So you see we get to excuse me, you see we get to octahedral, and we have 1, 2, 3, 4, 5 options. So there's 5, 8, 10, 11, there's 14 options total. I am not going to make you memorize 14. If school ever reopens and we have a quiz or a test, I will tell you you are not going to have to know 14. Okay? There's only a couple that are more important. There's only a couple that I want you to focus on. So, if we go to our electron domains, so we have an AB2 molecule. All right, so we have 1 lone pair, so they're representing this as a lone pair. Right here, we get bent. So an example would be sulfur dioxide. 1 lone pair, they're bent. 4 electron domains, we have an AB3. We have tetrahedral. 1 lone pair, we get trigonal pyramidal. That's our ammonia, and you can kind of see this starts to make a pyramid. This starts to form a triangle, which is the base of a pyramid. If we go to, excuse me again, tetrahedral, an AB2, water is bent. We have 2 lone pairs. So the only difference between this bent and this bent is a lone pair. Now, we're using these single lines to represent, but this also may be a double bond or a triple bond. We don't know yet, because remember, it would still be 1 domain, even if that is the case. All right. Now, I can tell you water, you won't have a double bond, right? Because hydrogen won't have enough valence. It won't have enough electron shells for water, for electrons. So you see 5, 5, and 6, we have planar, pyramidal, linear again, seesaw shape, right? All these really convoluted shapes that lend themselves based on how the electrons fall. I'm not that far ahead yet. So what I want to do, I'm going to pause the video. I'm going to give you a couple of seconds to do these 2 examples. Sodium trifluoride and this polyatomic ion right here. All right, so try them, do your Lewis structures, your electron domains, and your molecular geometry. So hopefully you've tried these on your own, and let's see if you got what we got. So, molecular geometry for nitrogen. All right, we have 3 bonds because we have 3 fluorines, and 1 lone pair in the middle. So 1 lone pair on the central atom. Your molecular geometry is going to be trigonal pyramidal. All right. But what would its electron geometry be? Well, that'd be tetrahedral because we have 4 electron domains. So we get tetrahedral. Now what about this next one? This next one might be a little bit trickier for some of you, I don't know. But let's see. So we also have 3 bonds. We also have a double bond. Look at that. All right. So 3 electron domains on the central atom. 1, 2, 3. Carbon never should have a lone pair. All right. So we have 1, 2, 3 domains. And so trigonal planar and trigonal planar. Our electron geometry and molecular geometries both match in this particular case. All right. So hopefully you did those examples and no lone pairs. Okay. So this is why we have the different shapes that we have. So all electron domains repel each other. Okay. But different types will repel more or less. So a lone pair will absolutely repel everything. But single bonds won't really repel as much as double bonds or as triple bonds. So if you remember the charts, right, this lone pair right here, because there is a lone pair there, wants to be as far away from these single bonds as possible. But these single bonds don't really mind being a little bit closer to each other. All right, same thing for this oxygen. This oxygen has some lone pairs. Look at the bond angle compared to these single bonds. All right, so these fluorines have lone pairs. They're going to be far away from each other, but these ones aren't as concerned. All right. So lone pairs will try to repel each other more than bonding pairs will. Okay, that's essentially all this is saying. All right, that if you have a lone pair, they're going to repulse everything more than any type of bond will. All right, and bonding pair, yeah. So all of that is just essentially showing why we get the different shapes that we get. So if I back up a little bit for you, back to the examples, I only have. So here, this is why we get these different shapes, because as you add lone pairs, these repulsions are going to increase. And so that's why the sky is actually linear, because these want to be as far away from any of this as possible. Okay? So these shapes actually come from a very logical place. They come from a fact of them splitting themselves in a way that makes sense for them. Even though for you guys, you may think this is weird and confusing. How do we get there? It's because they just want to separate themselves. So, I'll show you this in the last minute and a half here. So if we have an atom, so this is methanol, all right? If we have 2 central atoms, what do? Well, we treat it like anybody else, okay? So it's tetrahedral, and this is tetrahedral, but it has 2 lone pairs, so it's bent. So it actually looks something more like this. So we can actually do this with multiple central atoms. I will not have you do that, okay? Because, or if I do, it would be a very straightforward problem. But most of your practice problems will just have 1 central atom for the foreseeable future, okay? So there is some homework that I have attached on Google Classroom that I want you guys to do, and I put a due date and an open date for it. Okay? I will send out instructions on Classroom about homework for this as well, because there's going to be something else that I want you guys to do. I hope this makes sense for you guys. I hope you're kind of seeing this. A large part of this is kind of just memorizing on your own. All right? Bye.